So without further ado, you're here to see ROPInjector using return-oriented program for polymorphism and AV invasion.
Okay, thank you, Brian. Well, my name is Christos Xenakis, and I'm going to present you a new tool that we have developed in the University of Piraeus, ROPInjector, as said Brian, and this is a joint work of my colleagues George Poulios and Christoforos Ntantogian. What is actually return-oriented programming? ROP is an exploitation technique that allows an attacker to execute a sequence of a scene instruction named gadgets. Each gadget is a borrowed code that ends with the instruction return. A sequence of such gadget allows an attacker to perform arbitrary operation. It's like a collage, as you can see in the photo. What is the objective of our research? Up to now, ROP has been mainly used to bypass the non-executable memory defense mechanism, the known as DEP. In this work, we propose ROP as a polymorphic alternative and in order to achieve antivirus evasion. To see an example, we have one portable executable and one well-known shellcode, and with our tool, we create many different variations of the portable execution that bypass the antivirus detection. Our tool, how it works, it takes a benign portable execution and a well-known malware, transform the benign portable execution and includes also the malware within the portable executable, and we're not so sure if it is Merlin or if it's Albert. Why to use return-oriented programming for antivirus evasion? First of all, we use borrowed code, and this means it does not raise any suspicions. A possible footprint might be the instruction that we use to put the addresses of the ROP gadget into the stack, but we will see it later how we'll proceed with this issue. May transform any given cell code to a ROP-based equivalent, so it is a generic method or a generic tool, and may use different ROP gadget or the same found in different addresses to perform its work. So it achieves polymorphism. Let's have a quick overview of the malware, evolution, and the antivirus. Initially, the malware contains plain code, and the antivirus uses signatures in order to detect this code. Then we have simple obfuscation, and to detect the malware, the antivirus uses regular expression. After that, we have oligomorphism, which is encryption. The malware encrypts itself, and the antivirus uses static analysis and checks for writable code section to the portable execution to find possible malware. And finally, we have self-modifying code, which is named metamorphism, which the malware replaces instruction to other set of instructions, and the antivirus use dynamic analysis and behavior-based signature. What are the challenges of our tool? First of all, the new resulting portable execution should evade antivirus detection. Then, the portable execution, the produced portable execution, should not be corrupt or damaged. The tool should be generic and automated, and should not require a writable code section to mutate, because this is an alarm for the antivirus. Let's see the steps of our tool. First of all, the tool has to analyze the cell code. Then, has to find out ROP gadget in the portable execution. Then transform the cell code to the equivalent ROP chain, inject missing ROP gadget if required. If some gadget is not included in the portable execution, we have to inject it within the portable execution without raising any alarm, assembly the ROP chain building code to the portable execution, and then patch the new file. Let's analyze the first step, CellCode Analysis. This step aims to obtain all the necessary information in order to safely replace the CellCode instruction with gadgets. For each instruction of the CellCode, our tool needs to know what register it reads, writes, or sets, what registers are free to modify, its bitness, where it is a branch, and if it's a branch, where it lands, whether it is a privileged instruction, if it contains virtual addressing, and whether it uses indirect addressing mode. We don't like scaled index byte instructions. Why? Because they are complex. They use complex indirect addressing modes. Instructions like this one, we don't like them. So, why we don't like them? Because they are long, more than 3 bytes. It is unlikely to find gadgets with these instructions, are rarely reusable, so we don't need them, and reserve at least 2 registers. So what we are doing? We have developed a procedure, a function named unrolling. And what does this function do? It replaces the complex function we see here with a simple set of instructions that can be handled easier. So with unrolling, we achieve increased chances of finding suitable gadgets, and we have less gadgets to be injected to the portable execution. So we have shorter instruction and reusable gadgets. In the second step, we want to find ROP gadget in the portable execution. So first we search for returns instruction. Here I list 3 options of return instruction in the portable execution. And then we search backwards for about 20 bytes to find candidate gadgets. Our tool automatically resolves redundant instructions in ROP gadget in order to avoid errors during the ROP chain execution. It maximizes reusability of the found gadget and avoids to inject unsafe ROP gadgets, which unsafe ROP gadgets are gadgets that modify non-free register, are branches, write to the stack or modify the ESP, are privileged, or use indirect addressing mode. Now let's see how we transform the CellCode to the ROP chain. Initially, we translate the CellCode instructions to an intermediate representation. It's an abstract layer that we use for matching. Then we translate also the ROP gadget that we found in the portable execution to an intermediate representation. And then we found a mapping between these 2 intermediate representations, either 1-to-1 or 1-to-many. This is a snapshot of intermediate representation layer. What is? We take all the similar instructions and we group them in different classes, which we use them for mapping. Let's see an example. If we have this CellCode instruction, which belongs to this type of instruction, and this is the gadget that we found in the portable execution that is also belongs to the same group of instruction, we have 1-to-1 mapping. Now, if we have this instruction and the gadget instruction, here you can see we have 1-to-many, 1-to-2, which means we call the gadget twice in order to replace the CellCode instruction. Now, what happened if the portable execution does not include the required ROP gadget? If we simply put the ROP gadget, this will raise an alarm because of statistics. We have sequential return instructions. So we want our tool to insert ROP gadget in a benign looking way, which means scattered. And to do this, we use the caves in the TXT section of the portable execution, which are padding spaces left by the linker. Let's see an example. Assuming that this is the missing gadget, and we have found the cave that is presented in the slide. So we insert the instructions in red. As you may notice, the cave is reduced, but without cause any alarm. So we have the normal flow of the program, and we have also the ROP flow of the program. The last two steps, step 5 and 6, have to assemble and patch the ROP chain into the portable execution. Step 5, we have to insert the code that loads the ROP chain into the stack using push instruction. And the step 6, we have to extend the TXT section and repair the relative virtual addressing and relocation. Our tool includes two different modes, two different methods to pass the control of the to the ROP shell code. Run first, which runs more suspicious, or run last, which present better results. Here is the code before the injection, and here is the code after the injection. You can see the TXT section file is extended with our ROP chain. Then we have to modify the index to the memory in order to the file to operate. And if we find a certificate, we erase it, and we recalculate the checksum. As I said, there are two options to pass the control to the malware. The one is first run first, which raise alarms, and we have tested this. And the second is run last, which presents very, very nice result. Actually, we try to find exit process, and then we put before the exit process a jump to the malware. Let's see the evaluation of our tool. ROPInjector is implemented in native C. We have used it and tested using 9 portable, very well-known portable execution applications like Firefox, Java, Acrobat, and all that stuff. We have carried out a combination of scenarios, like we have tested the original file without any patching, without nothing. A ROP shell code that is executed at the exit of the portable execution. The set code intact, without any modification, that is also executed at the exit of the portable execution. And this is the third case, presents very, very interesting results. Another scenario is the ROP shell code that is executed first after a delay of 20 seconds, and the set code intact. For our evaluation, we have used two very popular Metasploit payloads, the reserved TCP shell and the Metaprote reserved TCP shell. And we have tested our transform, let's say, portable execution to the VirusTotal. That includes 57 antiviruses. Here is the result for the reserved TCP shell. As you can see with the gray color is the original file that contains no virus, so it passed from all the antiviruses. With green, we have the ROP with the exit. the outcome of our tool that includes a shellcode and activates the shellcode during the exit of the portable execution. As you can see, we have approximately 100% evasion. In the third column, we have the third bar, we have the shellcode intact without any modification that is executed during the exit procedure of the program. And we feel surprised to see this result. When we activate the ROP shellcode at the beginning of the program, after a delay of 20 seconds, I can say that the result was about 50%, so they're not very, very good. And finally, the red one is the shellcode itself. These are the results for the interpreter reserved TCP. It's even better. So, we achieve, at most of the cases, 100% we bypass antivirus detection. On average, we have 99.31. The outcomes of this work. Signature-based detection can be bypassed by techniques like ROP shellcodes, like the techniques that we propose in this work. Behavioral analysis also can be bypassed by techniques like running right before the exit process. And checksum and certificates provide poor protection. As we see, we can recalculate or erase the certificates and nothing happened. So, our proposal, the outcome of this, the early outcome of this work, because it's a work in progress, we propose the engagement of certificates and checksum, the enhancement of behavioral analysis, and the execution, last but not least, the execution of behavioral analysis until the program really ends. So, this is the presentation of my tool. Thank you very much. Questions?
I've got a quick question. In the middle, right here. Hard to see, I know, the lights. I want to know whether anyone's looked into, on your team, writing the shell code in your intermediate representation to make it even easier.
No, we haven't.
It's probably a lot of work.
Yeah. Actually, we have tested some. We made some tests to see how effective are the antivirus, and that's why we come with this tool. But as I said, it's a work in progress. So we want to try and see more issue in this area, it's a very interesting area. Sorry, if there's any other question, I cannot see because of the lights, and I wear glasses, so it's really hard for me to. Any other question?
Hi. I was just a quick question regarding your results. Do you know why there's a big difference between the two shellcode scripts? The first one seemed to have a higher evasion rate than the second one. Is it because of the instructions it generated, or was it just longer, or was it?
Actually, we haven't checked. We have to see the difference of the two cell codes to see why this happens, but we haven't done this yet because it's very complex. It's one project by itself to see which different instructions raise alarm and how the gadgets, it's all the semantic behind the instructions. So it's a hard work. But we plan to make more experiments and investigate more correlations.
Yes, sir. Have you tried to run this combined with the MSF encodes?
No, we haven't yet.
Thank you.
Yes.
Here's a question. Have you tried the executables that you generated with standard anti-ROP tools like EMET, for example?
No, we have not tested. Because we use portable executable that everybody uses. It's our tool comes with the result that if we use well-known portable execution that enable ROP, we can hide the cell code inside this code without bypassing the antivirus detection.
The reason I asked is that ROP is a dynamic exploitation technique, and antiviruses are predominantly using static analysis. So it shouldn't be expected that antiviruses, especially in VirusTotal, which are sort of castrated versions running from command line. But dynamic analysis tools like EMET, host intrusion protection systems on real machines should be able to catch this type of stuff more effectively, definitely more effectively than VirusTotal battery of command line castrated scanners.
Yeah, but as you see in this slide, we have 88% of the simple cell code injected to the file at the exit. So it's possible that this behavioral analysis is not activated or is not so effective. That's why we come up with the result that the antivirus should activate and utilize until the end of the program the behavioral analysis and the behavioral signatures. Any other question? Okay, thank you very much.